Hi everyone. So we've been able to derive the expressions for step response RC and step response RL circuits. In this video, we're going to try and solve a couple of problems on step response RC. The next one will take step response RL circuits before we move on to RLC circuits and eventually Laplace and Fourier transforms. So we have four problems to tackle in this video. So let's get right to business. The switch in the circuit has been at A for a long time. At t equals 0, the switch moves to B. Determine V of t for t greater than 0. Okay, so we have a single pole switch with two throws. Okay, so we have a single line here that can either be at A or at B. So where it is depends on which circuit is being active. So at t less than 0, we're told that the switch has been at A for a long time. When you see for a long time, that is what it's trying to tell you is that your capacitor has become fully charged. Alright. So at t less than 0, our switch has been at A. So that means this part of the circuit gets completed. The 24 volts, 3k ohms, 5k ohms, along with our capacitor over here. At t equals 0, the switch moves to B. So once t equals 0, the switch, like as the arrow shows, comes to here and completes this circuit instead. Okay, leaving this whole part redundant once t equals 0. So that means what we're going to analyze once t equals 0 is going to be with our capacitor, the 4 kilo ohms, and the 30 volt source. And we're supposed to determine V of t, the expression for V of t for t greater than 0. So that's what we can do. Obviously, we're going to start with t less than 0. So we're going to analyze our circuits at t less than 0. Remember, we're told that our switch has been at A for a long time. That means our capacitor becomes fully charged. I remember, once your capacitor is fully charged, you end up with an open circuit. So a fully charged capacitor is an open circuit. Okay, but a fully charged inductor becomes a short circuit. This is very important for analyzing circuits and determining conditions. So let's redraw our circuits for t less than 0. We have a 24 volt source somewhere here, plus, minus, going this way, 3 kilo ohms. And then we close our circuits nice and easy. This 24 volts, 3 kilo ohms, and 5 kilo ohms, 5k. Alright, so our capacitor is fully charged, meaning it's an open circuit. So we can sort of do it this way. Okay, to kind of show, our capacitor is still here. Even though it's an open circuit, we're still going to have an open circuit voltage. Alright, so let's call this V0, since that's what it's going to be. You can see now that, V0 is in parallel with, the capacitor is in parallel with the 5k. So the voltage across the 5k is going to be the initial voltage of the capacitor. So what we're going to use is what we call voltage divider principle to determine V0. So how that works is that you have a resistor, once you get voltage up, that's 5k. So that's going to be on the numerator. So 5k, okay, let's do 5k over the sum of the resistors. So that's 3k plus 5k. That's 8k. Okay. So 5k over 8k. Okay, it's cancelled out. Then over the total voltage that is going to be the sum of the two. This 24 volts is the only source we have here. So the sum of 3k, the sum of the voltage across 3k, sum of voltage across 5k is definitely going to add up to 24 volts. That's Kirchhoff's voltage law. So times 24. That's going to give us V0. So that's 5 over 8 sine 24. That's 15 volts. So very simply, we've shown that, the V0 in our circuit, initial voltage in our circuit is 15 volts. That means we're through with t less than 0. We're through analyzing for t less than 0. The next thing we're going to do is step up to, t greater than 0 once our switch moves to B. Okay, so our switch is at B. Let me draw an extra line to safety. Alright, so for t greater than 0, we have our capacitor, 4 kilo ohms, and then our 30 volts. Now we're working with the 30 volt source, plus minus 30 volts are is 0.5 millifarads and 4k ohm. All right, the first thing I like to do is to find the Thevenin resistance, R Thevenins. This is going to help us find time constant. So to find the Thevenin resistance, you turn off your sources. So voltage sources become short circuits. Current sources become open. So if we were to make this a short circuit, make this just a short circuit, we'll be left with the 4 kilo ohms. That's the only thing that's going to be after the capacitor terminals. So that means R Thevenin is, very simply 4 kilo ohms. And remember, the time constant for RC circuits is RC. So we're going to do 0.5 M. This is M is milli. So that's 10 to minus 3 times 4K. Okay, so kilo is 10 to the power, 10 raised to power 3. So these are going to cancel out. So we're going to have 4 times 0.5, and that is 2 seconds. So at tau, our time constant is going to be 2 seconds. Okay, which is very simple. So you can see we're stacking up what we need for our circuits. For step response RC, we're going to need 3 major elements. Okay, V0, the initial voltage, the time constant, and eventually V infinity. So let's try and work for V infinity. So for V infinity, to solve that, we're going to assume time as time tends to infinitely far into the future. Once the capacitor has fully discharged itself, it's charged up with V0 at t equals 0, it's going to start dissipating, and at t tends to infinity, it's going to fully become an open circuit again. So once that happens, you're going to have deal with an open circuit again. Plus minus, open, and this is going to be your V infinity. All right, 4 kilo ohms, 30 volts. So current doesn't flow. Current can't flow in this circuit because of this open jump, meaning there's no voltage across the 4 kilo ohms. A resistor is going to need current flowing through it to create a voltage. That means this V infinity is going to be exactly the 30 volts. It's as simple as that. So V infinity is 30 volts. So these are just the main 3 tools we need for dealing with step response RC. Your V infinity, the time constant, and your initial voltage. So the last thing we're going to do is, put everything together. If you remember the formula, voltage as a function of time is going to equal V infinity, right? Plus, then open a bracket, V0 minus V infinity, e to the minus 2 over time constant. This is in volts. V infinity is 30 volts, so we're going to start substituting 30 plus 15 minus 30, e to the minus t over 2 volts. All right, 15 minus 30 is minus 15. T divided by 2 is 0.5 times t. So we're going to end up with, very nice, very simply, very elegantly, our voltage as a function of time is going to be 30 minus 15 e to the minus 0.5 t volts. So that's as simple as it gets. It's just to make sure you're analyzing your circuit properly. Starts with t less than 0. Okay, we saw that our capacitor becomes open. It shares the same V0 as the 5 ohms. We did a voltage divider to get V0. Our switch opened. Once t equals 0, you solve for your Thevenin resistance. That helps you get your time constant. Take note, I didn't make the capacitor an open circuit here because this is once t equals 0, once switching happens. Then to get your V infinity, you take time as it tends to infinity, the limits to infinity, and then you usually get the voltage at the source. All right, so let's move on. This is the second question. The switch in the circuit has been closed for a long time and is opened at t equals 0. Okay, so these are switch in the circuit. It's been closed for a long time and is open at t equals 0. Find I and V for all time. So, a couple of things are different here. Now we're dealing with a single pole, single throw switch. Is either closed or open. So it was closed and then it gets open. Now we're also asked to find I and V for all time. This is R. V is the voltage across the capacitor, and I is the current leaving the 10 ohms resistor. All right, so let's try and make a little analysis before we start solving. The switch has been closed for a long time. So let's say when this is closed, all right, we're analyzing for t less than 0. Everything in the circuit is involved. But if you take note here, you see that this voltage is 30 U of t. Remember what we said about the unit step function? I described it in the step response RC derivation. I'll link that in the video. Okay, the unit step function helps us know when a source is or isn't active in the circuit. So for t less than 0, since this is 30 U of t, this is not active. We have 0 volts over here. So this becomes a single straight wire, and we're just left with the 10 and 20 ohms in parallel. All right, once this opens, this becomes purely 30 volts. So for t less than 0, we're dealing with our 10 volt source. For t greater than 0, we're dealing with our 30 volt source. So let's get to solving and see how that helps us solve matters. So for t less than 0, recall we said the unit step function makes this tend to 0. Let me just clarify that. So for u of t, okay, its value is 0 for t less than 0 and 1 for t greater than or equal to 0. So since we have 30 u of t, all right, so if we're dealing with t less than 0, it's going to be 30 times 0. That's 0 volts. So this is 0 volts for t less than 0. So let's get to work. For t less than 0, for t less than 0, let's try and redraw a circuit. We're going to end up with very simply, this is 10 ohms, this is 20 ohms, this is our capacitor, and this is the active source. This is 10 volts. All right. Because this is an active, so this is 10 ohms. I of t is the current leaving here. This is 20. This is 0.25. That's 1/4. All right. And this is 30 volts. All right. So what do? We're looking for, at t less than 0, what are we looking for? V0. V0, the initial voltage across the capacitor. So remember, t less than 0 is enclosed for a long time. Our capacitor becomes fully charged, becomes an open circuit. So we can transform this to an open circuit and make V0 the voltage across it. Okay, so that's V0. So what do you see here? Everything here is in parallel. The 10 ohms is in parallel with the 20 ohms, is in parallel with the arbitrary V0, which is in parallel with the 10 volt source. So we don't even have to do much work. V0 is simply and straightforwardly 10 volts. That's it there. It's in parallel with the 10 volt source, therefore the voltage across it is 10 volts. It's as simple as that. Now, before you jump on, remember we are being asked to find I and V for all time. That means since we're dealing with t less than 0, we also got to get the current at t less than 0. So, this isn't even hard. You're not going to divide anything because you're given voltage. So the same voltage across the 10 ohms is the same voltage across 20 ohms. So we call Ohm's law. I is V over R. Okay, so that's going to be voltage across this is 10. That's 10 volts over 10 ohms as 1 amp, which is amazing and is absolutely correct. But you've got to be careful with what you're given. All right, this Ohm's law, look at the polarity of our source. It's going this way. So current leaving this 10 volt source is going to flow in this direction, meaning this 1 amp that we just got is flowing this way. Since we're given explicitly the direction for I of t, we've got to make I of t negative to what we solved for. I hope that was clear. So therefore I of t for t less than 0 is equal to minus 1 amp. Okay, let me see if I can explain. You've got Ohm's law. Alright. Let's see what this was. Plus, negative. And you've got a resistor here. It's a very simple case. Let's call this 10 ohms. Let's call this 50 volts. Alright, say we were asked to find, alright guys, what is IA? Let's call this IA. What is IA? Ohm's law is very simple. I is V over R. Okay, so we're going to do 50 over 10, which is 5 amps. That's the current flowing this way, which is amazing. If, however, we were given IA to be flowing in, IA flows in this direction. Okay, that means IA is leaving the 10 ohm source and leaving the 10 ohm resistor and entering the 50 volt source. All right, you're not going to panic. You're going to solve what you know as Ohm's law. Okay, you're going to solve locally, saying, all right, I naturally will have current flowing this way. Okay, I can even call this, let's call this I naught. So my I naught is normally going to be V over R. So my I naught is going to be 50 over 10, which is plus 5 amps. Okay, but since I naught is flowing negative to IA, you're now going to say, all right, IA is negative I naught, which is minus 5 amps, which is exactly what happens. Ohm's law isn't being violated. Nothing is changing. It's just the polarity of the signs we're given. So since we're given explicitly the direction of I of t, we've got to respect their decision and solve accordingly. So since we've gotten V naught and we've gotten, let me highlight this. We've gotten V naught and we've gotten I of t for t less than 0. That means we can, move on to t greater than 0, see what this question has got in store for us. So now I'm solving for t greater than 0. Our switch opens now. 10 volts is active, and our 30 volts source, comes back into action. Let's withdraw this and see what happens. Okay, 30, 10, and 20, and 1 over 4 farads. All right, very simple and short. The first thing we do once we're looking at t greater than 0, once switching happens, is to look for our Thevenin resistance, R equivalent. To do that, we turn off the source. We turn off the voltage source. The voltage source comes to short circuit, short circuit this way. And 10 and 20 are in parallel. So R Thevenin is going to give us 20 and 10 ohms in parallel. And stuff, this is very simple. We're going to do, products over sum. Is a neat way to skip the mathematics. You want to find the equivalent of two resistors in parallel. You do their product, RA times RB, all over RA plus RB. I'm going to say that work. So 20 times 10 over 20 plus 10. 20 plus 10. That should be, our Thevenin should be 200 all over 30. Which is 5 over 3. 20 over 3, pardon me. Okay. Let's cancel that. 20 over 3. 20 over 3 ohms. Alright, which is amazing. The next we're going to do is a time constant. For RC circuit is, R times C. So we're going to do 20 over 3 times 1 over 4. 4 here, 5. Our time constant is going to be 5 over 3. 5 over 3 seconds. I believe that's 1.667. Alright, which is amazing. We found our time constant, which is the second major thing we need. Alright, let's even highlight it. So our time constant is 5 over 3 seconds. And this is 3, not 8. Pardon my handwriting. Okay. The next thing we're going to do is, find V infinity. Or find V infinity as t gets infinitely far into the future. What's going to happen to our voltage? I don't like the way the sign looks. Alright, let's get to work. So as t tends to infinity. Oh my. Are we good? Alright, I think we're good. So for t tending to infinity. Alright, remember, t less than 0, a capacitor fully charged becomes an open circuit. T equals 0, once switching happens, a capacitor is still active. Okay? The capacitor is still active over here. t tending to infinity, our capacitor has fully discharged, becoming an open circuit again. It's a very cyclic process. So that means this becomes an open circuit. We still have our 30 volts source over here, 10 ohm resistor, and our capacitor becomes this is going to be infinity. 20, 10, and 30 volts. And make this volts. Alright, ohms. Do I need ohms? Perhaps for professionalism. A little bit. 20 ohms. Okay. So what do we do here? I hope things are getting a little bit familiar now. Now we're looking for V infinity, and we can see that our capacitor was in parallel with the 20 ohm resistor. We are going to voltage divide again. Remember what we said from the first question. So V infinity is going to be the same as the voltage across the 20 ohms. Okay, which is going to be 20 over 20 plus 10, that's 30, times the total available voltage, that's 30 volts. So this cancels out, and our V infinity becomes 20 volts. Oof. How did these keep on happening? Okay. So this is our V infinity. So you can see we have everything we need to wrap up our circuit solution. Alright. Remember, recall V of t is equal to V infinity I'm going to give myself a little bit of space. So V of t plus V naught minus V infinity e to the minus t over time constant volts. Our V infinity is 20 volts. We'll start off with that. So that's 20 plus V naught is 10 volts. So that's 10 minus 20 again. E to the minus t over 1.67. All in volts. So doing 1 over 5 over t is going to give us 3 over 5. That's 0.6 recurring. So V of t is going to give us 20 minus 10 e to the minus 0.67 times time volts. Which looks like we're done. It looks like we're done, but we've got to remember the question asks us to find I and V for all time. Alright, and we need to do for I. This is going to be a very important concept. Okay, it's going to be a very important concept. Remember we solved for our V naught was what again? Was 10 volts. Okay? Our voltage as a function of time was 20 minus 10 e to the minus 0.67 volts. Okay? Our I naught was minus negative 1 amps. And we need to find I as a function of time, to be able to evaluate it for t greater than 0. So what are we going to do here? Let me redraw the circuit because I can't write over that. 10. I'm redrawing for t greater than 0. So, we have a 10 ohm resistor, 20 ohm resistor, capacitor, voltage source, plus minus 1 over 4 farads. I believe this is 20, this is 10, this is 30 volts. Alright, so what's going to happen? We have I of t flowing in this direction. We have the expression for this voltage, V of t. Just repeating it. I should write more clearly. Alright, so what are we going to do? We're going to make use of Kirchhoff's current law, which means that we're going to make an analysis of at this node. Okay, to be able to find this. This is I of t. Okay, and we're going to work backwards. We're not going to directly solve for I of t, but we know that I of t, let's call this I20. Let's call this IC. Okay, so we know that the current entering this node is going to be the sum of the current leaving the node. So since we have an expression for this voltage, and we know that this guy is in parallel, we can, get this current, the capacitor current, get this, the 20 ohms resistor current, and sum it together. And that's like reverse engineering our way back into solving for I of t. So we're going to establish that I is going to be I20, by I20 I mean current to the 20 ohm resistor plus current to the capacitor. Alright? Remember, current is voltage over current voltage over resistance. So that's going to be whatever we go for V of t divided by 20. So that's 1 over 20. And let me just do it. So that's 20 minus 10 e to the minus 0.67. Alright. This is our voltage. Over 20 ohms. This is our resistance. And our capacitor current is going to be, we call C divided dt. Okay. Remember, capacitor current is C divided dt. That's what we're going to use here. So we're going to do C. That's 0.25. Okay. Alright. Then we're going to differentiate this voltage as a function of time. Okay, relax. It's not a big issue. We have 20 minus 10 e to the minus 0. There's a decimal point here. 0.67. This is a constant. So differentiating this, if V of t is 20 minus 10 e to the minus 0.67 volts. Okay, differentiating this, d V of t dt. Alright, this is going to go. There's no constant. This is going to go. There's no constant here. So we're left with this. So we take out the constant. So that's minus 10. Okay, and we bring out, okay, this is time. Let's not forget time. 0.617. Okay, and then we bring out the coefficient of the variable that is in the exponent of e. Okay, we have Euler's number here. We have an exponent here. Our variable is inside the exponent, and the coefficient is minus 0.67. So to differentiate this, we bring it down. Okay? Bring it down. Minus 10, minus 0.67. Alright? And then multiply it with everything as it was, e to the minus 0.60. Which is exactly what we're going to do. Alright, so let's have a bit more space when we're working. And we're working here. Alright, so that's I20. And let me do that. 1 over 20 times 20 minus 10e to the minus 0.67 times 10 plus this whole I of c is C divided dt. Okay. So plus our capacitance is 1 over 4. C. Then divided dt. Then that's this entire expression over here. Minus 10 minus 0.67 and e to the minus 0.670. Alright, so to simplify this, what do we get? For lack of time, this is correct actually, but let's run through this. That's 1 minus 0.5 e to the minus 0.670 plus 1.5 e to the minus 0.67 t. Alright, so that's 1.5 this minus 0.5 this. And I as a function of time is going to be 1 plus e to the minus 0.672. Because 1 is going to be the coefficient of this 670. Alright, so to write how we write these solutions is what you call a piecewise function. Since you're breaking it down into t less than 0 and t greater than 0. Let's do that for V of t. Remember we said that V naught was, what's V naught again? Was 10 volts. Alright. And V as a function of time was 20 minus 10 e to the minus 0.670. Wow, I've said that a lot today. So this is going to be, so you're now going to say v as a function of, for all time, we're going to draw a piecewise function. This first half is going to be for t less than 0. So that's 10 volts for t less than 0. Then what our expression, 20 minus 10 e to the minus 0.67 t for t greater than equal to 0. That's how you express solutions for all time. So for I of t, alright, we got I naught to be negative 1 amps, and I as a function of t to be 1 plus e to the minus 0.67 t. Wow. I have said that a lot today. So, writing this as a piecewise, I of t is negative 1, t less than 0, 1 plus e to the minus 0.67 t. For t greater than 0. Ta-da! That's what we have. This is a really, really long solution. But it's really not that complex. You just have to keep your eyes on what you're doing, especially. Be careful for the signage of this for I of t. And then, solve for t less than 0, for t greater than 0. And remember to find I of t. We worked backwards and said, all right, since that is going to be the sum of the 20 ohms current and the current to the capacitor, why not just sum that up and get our total sum?